Voyager 1 is still transmitting. That single fact has been sold to you as triumph, as proof that something we built in the 70s refuses to die. But the signal arriving on Earth right now left the spacecraft more than 23 hours ago. It came from a machine running on a plutonium heart that has lost nearly half its power. It crossed a region of space NASA never designed it to survive. And the deeper you look at what that signal actually is, the harder it becomes to call any of this a success. Voyager 1 is not exploring. Voyager 1 is bleeding out, and the silence is already scheduled. That is the part nobody puts on the press release. Voyager 1 is the farthest human-made object from Earth, but farthest is not the same as far. Farthest is a ranking. Far is a measurement against where you were trying to go. And when you measure Voyager 1 against the actual structure of the universe it is supposedly entering, the picture changes badly. Here is the thesis. The official story is that Voyager 1 is humanity's farthest ambassador, a triumph of engineering still doing science in interstellar space. The harder reading of the same facts is that Voyager 1 is a dying probe whose continued operation has been quietly obscuring how little reach we actually have as a civilization. The press releases are not lying. They are choosing which truths to amplify. Voyager 1 sits roughly 166 astronomical units from Earth, about 24.8 billion kilometers. The people running this mission are not really operating a spacecraft anymore. They are writing letters to one. Every instruction is mailed into a dark room, with no way to know if the room is still there when the letter arrives. The only confirmation that Voyager 1 is alive is the signal that left it a day ago. They are talking to a ghost on a 46-hour delay, and the delay only gets longer. That distance, the one that sounds so impressive, is the same distance that proves how small our reach really is. NASA declared Voyager 1 had entered interstellar space in 2012. Most viewers pictured a small craft sailing into a vast new ocean, finally free of our solar system. That image is wrong in almost every way it can be wrong. What actually happened is that Voyager 1 crossed the heliopause, the edge of the bubble of charged particles blown outward by the Sun. By that technical definition, yes, Voyager 1 entered interstellar space. By the definition most people heard, where interstellar means on the way to another star, it did nothing of the kind. The nearest star, Proxima Centauri, is about 4.24 light-years away, roughly 268,000 astronomical units. Voyager 1 has covered 166 astronomical units in 48 years. That is 0.06% of the distance to the nearest star, 0.06%. Imagine the distance from the Sun to Proxima Centauri scaled down to the width of the United States, coast to coast. On that scale, Voyager 1 in 48 years has crossed roughly the length of a suburban driveway. Not a city block, a driveway. With Los Angeles still 4,000 kilometers ahead, and the spacecraft already running out of power. If you extrapolate its trajectory, Voyager 1 will pass within about 1.6 light-years of a star called AC plus 793888 in roughly 40,000 years. Older than recorded history, older than the cave paintings at Lascaux, and it will not stop. It will not transmit. It will just drift past, dead and silent. The Oort cloud begins around 2,000 astronomical units. Voyager 1 has not even reached its inner edge. It will not exit the Oort cloud for something like 30,000 years. By every meaningful definition of leaving the solar system, it has not done it. It is still inside our front yard, just past where the porch light reaches. The word farthest was never really a description of reach. It was a description of absence. Voyager 1 is the farthest human-made object, not because we pushed the limits, but because we have not built anything faster behind it. New Horizons, launched almost 3 decades later, is slower at the equivalent distance from the Sun. The fastest interstellar trajectory ever achieved was set by a spacecraft that launched the same year Elvis Presley died. And we have not beaten it since. When a record stands for 48 years in a field defined by continuous progress, that is not a record. That is a ceiling. Voyager 1 does not run on solar panels. At 166 astronomical units, sunlight is about 27,000 times weaker than on Earth. So Voyager 1 runs on 3 radioisotope thermoelectric generators packed with plutonium-238. The mechanism is almost embarrassingly simple. The plutonium gets hot on its own through alpha decay. That heat hits an array of thermocouples, which produce electricity when one side is hotter than the other. Hot plutonium on one side, cold space on the other. That is the entire mechanism keeping Voyager 1 alive. A campfire and a sled. Plutonium-238 has a half-life of about 87.7 years. The decay is exponential, not negotiable. At launch, the 3 RTGs produced about 470 watts. Today, they produce roughly 225 watts, losing about 4 watts every year. 225 watts is less than an old incandescent bulb, less than a hairdryer on its lowest setting. With that, Voyager 1 has to run its computers, heat its fuel lines so the hydrazine does not freeze, power its transmitter, maintain its memory, keep its scientific instruments alive, and broadcast across more than 22 light hours. The math has been failing for decades. The mission has only stayed alive because engineers have been turning things off. This is what the press releases call graceful management. It is triage. The cameras went dark in 1990. The ultraviolet spectrometer was switched off in 2016. In 2024 and 2025, the cosmic ray subsystem and the low-energy charged particle instrument were placed on the shutdown schedule. One by one, the senses of this spacecraft are being amputated to keep the heart beating a few more years. The current best estimate is that Voyager 1 will lose the ability to power any science instruments around 2025 or 2026. The spacecraft may send a basic engineering heartbeat for a few more years. By the early 2030s, even that will likely stop. The official language calls this approaching the end of the mission. A more honest reading is that the patient is in hospice. The thrusters on Voyager 1 are small. Each produces about 1/10 of a pound of thrust, roughly the force of a sheet of paper resting in your hand. They run on hydrazine. When one fires, a brief puff of gas nudges the spacecraft a fraction of a degree, just enough to keep the antenna aimed at a small blue dot 24 billion kilometers away. That is the entire system keeping Voyager 1 in contact with humanity. The high-gain antenna must be pointed within a fraction of a degree of Earth for the signal to be detectable at all. A small drift, and the entire link goes silent, permanently. And those thrusters are clogging. Over decades of firing, the hydrazine has been depositing silicon dioxide, the same compound that makes up sand and quartz, on the inner walls of the propellant tubes. The deposits are microscopic at any given moment, but they accumulate. Year after year, the tubes get narrower. In 2017, engineers woke up a set of backup thrusters that had not fired since 1980. 37 years of dormancy. They sent the command, waited the 20-some-hour light delay, and the thrusters fired perfectly. Press releases praised the resilience of 70s hardware. Here is what the celebration obscured. Those backup thrusters were not woken up because the team was curious. They were woken up because the main thrusters were already failing. The 2017 firing was a workaround, and spare tires do not multiply. In 2024, the same problem returned. The thrusters, woken from a 37-year sleep, had themselves accumulated enough clogging that engineers swapped to yet another set. The spacecraft is on its third generation of thrusters, and the third generation is also going to fail. The failure mode is not about any individual thruster. It is about the design of the system. Every set is connected to the same plumbing, the same chemistry, the same slow accumulation. The clock is identical for all of them. Now think about the antenna. Voyager 1's high-gain antenna is 3.7 meters across, locked rigid to the spacecraft body. To point it at Earth, the entire spacecraft must rotate. And the only mechanism capable of rotating it is the thrusters, which are clogging. If the thrusters fail before the power runs out, the spacecraft will still be alive, still generating electricity, still capable of speech, but it will be talking in the wrong direction. Voyager 1 could transmit for years after we have already lost contact, a monologue into the dark. Here is the assumption almost everyone makes. If we built Voyager 1 in the 70s, then with modern technology, we should easily build something that goes twice as far, 10 times as far. The intuition is linear. It is not how this works.
The first wall is the inverse square law. The strength of a radio signal does not decrease linearly with distance. Double the distance and the signal is 1/4 as strong. 10 times the distance, 1/100th. The signal spreads outward in a sphere, and the surface area of that sphere grows with the square of the radius. There is no way to defeat this with cleverness. Voyager 1 transmits at about 23 watts. By the time the signal reaches us, it is around 10 to the minus 23 watts, about 20 billion times weaker than a cell phone in your pocket. The dishes that pull this out of the noise have receivers cooled to near absolute zero. Now imagine a probe at 1,000 astronomical units, 6 times farther than Voyager 1. The signal would be 36 times weaker. At 1 light year, it would be 144,000 times weaker. The current data rate from Voyager 1 is about 160 bits per second, slower than a 1984 modem. Push the spacecraft farther and the rate collapses. The mission ends not because the probe stops working, but because the universe makes its voice too quiet to hear. Could we build a bigger antenna on the spacecraft? Marginally. But every additional meter adds mass, which requires more propellant, more launch vehicle, more money. Double the antenna, gain a factor of 4. Go twice as far, lose a factor of 4. You have broken even and spent billions doing it. Could we build bigger dishes on Earth? The next generation deep space network has been on the drawing board for years. The Arecibo dish, 305 meters across, collapsed in 2020 and has not been replaced. The infrastructure we use to listen is shrinking, not expanding. Then there is propulsion. Voyager 1 moves at about 17 kilometers per second relative to the Sun. It got that fast using gravity assists around Jupiter and Saturn, a rare planetary alignment that occurs once every 176 years. We caught the window. We will not catch it again in our lifetimes. Breakthrough Starshot, the most ambitious current proposal, imagines firing a 100 gigawatt laser at gram-scale probes to push them to 20% the speed of light. The technology required does not yet exist. The probe would have no meaningful payload and a transmitter so weak that receiving its data would require an array larger than anything we have ever built. The kinetic energy required scales with the square of velocity. Push a 1-ton spacecraft to 10% the speed of light, and you need roughly the annual output of a large nuclear power plant, delivered in a sustained burn. The Saturn V was the most powerful machine humans ever built, and it barely threw 3 people 1¼ light seconds away. The fantasy is that we are between Voyager 1 and the next step. The reality is that Voyager 1 is the step, and we have been standing on it for almost half a century. Deep space is not empty. The picture in your head, the black vacuum dotted with distant stars, is a lie of scale. At the scale of a spacecraft, the space between stars is full of high-energy particles and radiation. Voyager 1 is drifting through a corrosive ocean. A cosmic ray is a particle, usually a proton, accelerated to nearly light speed by some violent galactic event. Earth is shielded by the heliosphere and our magnetosphere. We do not feel them. Voyager 1 has left that protection behind. When it crossed the heliopause in 2012, the cosmic ray flux jumped by about 9%. Every second, particles moving at nearly light speed slam into its hull, its circuits, its memory chips. Each carries enough energy to flip a single bit, to change a 1 into a 0, to rewrite code mid-execution. In May 2022, Voyager 1 began sending telemetry that made no sense. The orientation data was nonsense. For months, the team diagnosed the problem from a 44-hour round-trip distance. In April 2024, they confirmed it. A single chip had failed, probably hit by a cosmic ray. The engineers wrote new code, rerouting around the dead chip. Press releases called it a remarkable rescue. Read it the other way. A single particle, fired across the galaxy from some long-dead star, hit a piece of 70s hardware and almost ended the mission. The next hit might not be so lucky. The same particle flux, quietly killing Voyager 1's electronics, is the same flux any human on the same journey would have to survive. And human beings do not survive it. Astronauts on the ISS, inside Earth's magnetosphere, still accumulate measurable radiation doses. A Mars round trip would expose a crew to the equivalent of a full-body CT scan every 5 or 6 days for 2 to 3 years. Push past the heliopause, and the dose is high enough to cause acute radiation sickness within months and lethal cancers within years. There is no shielding that scales. To meaningfully block the highest energy particles, you would need meters of dense material around the entire crew compartment. The mass required is tens or hundreds of tons. The propulsion to push that to interstellar speeds does not exist. So the spacecraft proving how dangerous interstellar space is for hardware has also been proving how impossible it is for biology. Voyager 1 is not opening a door, it is closing one. We talk about sending humans to Mars as if it is the next obvious step. Mars is roughly 2 light minutes away. Voyager 1 is 23 light hours away. The gulf is not slightly more shielding, it is the difference between your backyard and crossing the Pacific by swimming. The Deep Space Network is the part of this story almost no one outside NASA thinks about. It is also the part that, more than the spacecraft itself, will determine when Voyager 1 actually goes silent. The DSN is exactly 3 sites on Earth, placed roughly 120 degrees apart in longitude so that as the planet rotates, At least one is pointed at any given target. Goldstone in the Mojave, Madrid in Spain, Canberra in Australia. The biggest dishes are 70 meters across. The 70-meter dish at Goldstone was built in 1966. They are older than the spacecraft itself. When Voyager 1 launched in 1977, the DSN had a manageable workload. Today, the same three sites support Mars rovers, the Parker Solar Probe, Juno, New Horizons, Europa Clipper, Bepi Colombo, James Webb, Artemis, asteroid sample returns, and dozens more. Every mission competes for the same antenna hours. Voyager 1, with its slow data rate and fading signal, is at the back of the line. When Voyager 1 launched, the team numbered in the hundreds. Today, it is roughly a dozen people. The original code runs in an assembly language for a custom architecture that no longer exists anywhere else. The engineers who wrote it are mostly retired or dead. The current team maintains the spacecraft using documentation that lives in paper files, in personal notebooks, in memories that have not been replaced. This is what institutional fragility looks like. Not a dramatic failure, a slow erosion. One day, possibly soon, the math will tip in a direction that has nothing to do with whether Voyager 1 is alive. The spacecraft might be transmitting perfectly, and there will be no one with the time, equipment, or institutional memory to receive it. This is what happened to Pioneer 10. Voyager's older cousin sent its last detectable signal in January 2003 from about 82 astronomical units. The official statement said the signal was too weak. That is incomplete. The funding had been wound down. The team had moved on. The spacecraft was not killed by distance. It was killed by a fading signal and an infrastructure that had moved on. Voyager 1 is on the same path. NASA's public timeline says it should operate into the mid-2030s. That is true if every assumption holds. Every assumption is fragile. Read enough NASA press releases about Voyager and a pattern emerges. Voyager 1 is still going strong. It is exploring interstellar space. The phrases get repeated. They are not false. They are not the whole story. Compare two documents. The public release announcing the 2024 thruster swap is full of words like ingenuity and remarkable. The internal technical briefing describes the swap as a necessary response to silicon dioxide clogging, with a note that the new thrusters are subject to the same failure mode. Both are accurate. One sounds like victory. The other sounds like a slow-motion equipment crisis. This is not deception. It is selection. Voyager 1 is the single most powerful symbol NASA has. Apollo is past tense. Voyager is present tense. Voyager is the only mission that allows the agency to credibly say, in 2026, that an American spacecraft launched almost half a century ago is still doing science. Losing it is losing the loudest argument NASA has for why deep space exploration is worth funding. Every press release emphasizing resilience is also a pitch to budget committees. This is not cynicism. It is how institutions communicate when their existence depends on public support. The problem is what gets crowded out. The instrument shutdown schedule, released in technical documents in 2024 and 2025, names which instruments will be turned off in which order. The schedule is not secret. It is not what press releases lead with. A fairness clause has to be said clearly. The engineers running Voyager 1 are heroes. They have kept 70s hardware operational for nearly 5 decades, at distances it was never designed for. The science is real. None of that is in question. The point is narrower. The public version has been smoothed until most people have no idea how close to the end it is. They hear "still going strong" and picture a thriving machine. They do not picture instruments being shut down on schedule, a failed memory chip nearly ending the mission, thrusters clogging, 12 people maintaining code in a language no one teaches anymore. Voyager keeps surprising us. That phrase reveals the structure. The engineers know what is degrading and at what rate. The surprises are surprises only to the audience. Take a step back. Voyager 1 launched on September 5, 1977. 48 years have passed. In those 48 years, every other domain of human technology has transformed. We went from the first personal computers to AI systems that hold conversations, from rotary phones to networked supercomputers in every pocket, from mapping one human genome at the cost of billions to sequencing entire genomes for a few $100s. And in the specific domain of how far we can send a spacecraft, we have done nothing. That is not rhetorical. Voyager 1 is still the fastest object ever sent on an outbound trajectory. New Horizons, launched in 2006, is slower at the equivalent distance. Nothing leaving the solar system has matched Voyager. Not with the Silicon Revolution, not with materials science, not with computation. None of it has produced a faster outbound probe than the one we launched when the average car had no rear seatbelts. If you saw a chart of human technological progress in any other field flat for half a century in the middle of an explosion of capability, you would call it a ceiling. The pause in deep space propulsion is the visible signature of a deeper truth. We never solved the propulsion problem. We solved a one-off trajectory using a rare planetary alignment, and we have been calling the result a milestone in a journey when it was the entire journey. The interstellar probe concept from Johns Hopkins proposes a mission that would reach about 1,000 astronomical units in 50 years. Technically feasible today, not funded. It sits in the queue behind every program that produces near-term political wins. Breakthrough Starshot proposes laser-pushed gram-scale probes that could reach Proxima Centauri in 20 years. The physics is possible. The engineering does not exist at the scale required. This is what stasis looks like dressed up as progress. The PowerPoint slides get more polished. The hardware that goes farther than Voyager 1 does not exist. We made one interstellar gesture almost half a century ago and have been generating concept art ever since. Apply this to the Fermi paradox. One increasingly serious solution is that interstellar travel is just much harder than the popular imagination assumes. Voyager 1 is evidence for this, not because it failed, because it succeeded, and its success defines the high watermark of what a determined civilization could achieve. And that mark is 1/1500th of the way to the nearest star. The last time any human left low Earth orbit was December 1972, Apollo 17, 54 years ago. Every person in space since has stayed in a thin shell no farther than a long road trip. The pattern is consistent. One burst of capability in the 1960s and 1970s, driven by Cold War urgency, followed by half a century of consolidation, retreat, and concept studies. The pattern is not acceleration. It is a single jump followed by a long plateau. And from the plateau, we have been telling ourselves stories about an exponential takeoff the data does not support. Voyager 1 is not evidence of human progress in space. It is the opposite. It is a quiet indictment of how little we have built since. So here is the verdict the stars already delivered. Voyager 1 is not telling us how far humans can go. It is telling us how far one machine, built in a specific historical moment by a specific generation, was able to drift before its makers ran out of money, time, and follow-through. That is the actual answer. Not a number in astronomical units, a measurement of a civilization. The plutonium clock is real, half spent, ticking. The thrusters are clogging on their third generation. The inverse square law is unmovable. The cosmic ray flux is killing the electronics and proving in the same data that no human body could survive the journey. The Deep Space Network is 3 sites in 3 deserts, oversubscribed, aging. The team is 12 people maintaining code in a language no one teaches anymore. And the fastest object humans ever built is still the one we launched in 1977. Voyager 1 is not going silent because it ran into the edge of what is possible. It is going silent because we made a series of choices year after year to fund other things. The cumulative shape is the situation we are in. 1 dying spacecraft, no successor. Half a century of stasis dressed up as progress. This should not land as despair. The Voyager mission produced data that reshaped our understanding of the outer planets, the heliosphere, and the interstellar boundary. The people who built it deserve nothing but admiration. The point is not that they did too little. The point is that we, as a civilization, did too little behind them. We sent the scout and never sent the army. When Voyager 1 finally goes silent, the honest reaction is not surprise. It is recognition. The grief should not be for the spacecraft. The spacecraft did its job. The grief should be for what we did not build to follow it. Here is where the narrow hope lives. The blueprints for the next mission exist. The interstellar probe study is real. The physics still permits a successor. The engineering is solvable. The only thing that does not exist is the decision. Voyager 1 will go silent. That ending is written. The only open question is whether anything follows it. That question is not for engineers. It is for us. For whether the gesture made in 1977 was the first step of a long walk or the only step we were ever going to take. There is an image I want you to leave with. Somewhere in the Mojave, the 70-meter dish at Goldstone is still listening. The signal it receives is weaker every year. One night, possibly soon, the dish will be pointed at the right patch of sky at the right time, and there will be nothing there. The engineers will wait. They will adjust the receivers, they will try again. And eventually, after enough silence, they will accept what the silence means. The spacecraft will continue drifting outward, dead and silent, carrying its golden record deeper into a darkness it can no longer report on. The press releases will say something graceful. And then the question Voyager 1 has been asking, quietly, for 48 years, will be the only thing left of it. Not how far it went, but how far we are willing to go. The honest answer is not in any astronomical unit. It is in the next budget. It is in the next vote. It is in whether the generation that watches Voyager 1 go silent decides the silence is the end of a chapter or the end of the story. Voyager 1 already did its part. What the next generation does is ours. And the dish, still listening to a sky that will eventually be empty, is waiting for the answer.